Hey, people. So this is maybe the easiest question that I gave in the review questions that I wrote today. You have a lot of questions in different level of difficulty. Starts from more tricky, quite tricky, into quite easy, and I think that might be the easiest. You have the exact formalization of this question in this page that I circled today. But a strip, how do I create a strip? I take two parallel lines and strip sigma. Small sigma is everything that lives between these two lines. All the points that are in below the upper line but above the lower lines of the strip. Okay? So it's like a line. How would I present it as Minkowski sum? It's another good question. What is a strip? It's a Minkowski sum of a circle, a disk, and a line that just passes the skeleton. So it's also a good review to remind you what is a medial axis. Medial axis is just what goes in the skeleton of the strip. Okay, I give you n strips. I'll give you one particular point Q, and I ask what is the depth of Q, which is how many strips contains Q. So for Q right here, the answer is only sigma 2 contains Q, so the depth is 1. Q is right here, the depth is 0. Point right here, the depth is 2, and I think that that's a maximum in this figure. In n square log n, give me the point with the maximum depth, a point with the maximum depth. You can meditate on it a bit as we are this finalized duality. And the plane, and my plan is to kind of go over the slides really quickly and see where people want me to stop. So, but we can also pay more attention to questions from the review or whatever you want me to do. So let's meditate on this a bit. Let's remind you what is duality. Maybe I should ask before the bureaucratic question about the midterm. You saw that we are doing it in our old room, 906. And you're allowed, people that know me, same as usual, which is 4 pages written on one side. The idea is just don't bring any solution to any homework you've ever seen or scratched on the web. Don't bring the textbook, but bring what you think is necessary. No limitation about fonts, how do you generate a script. So it's easily to counter my wishes, but it's up to you. And as you know, I like to give questions that are similar but not identical to homework questions. So they are different enough that if you cut and paste the solution from the homework, probably I'll find it, but they are similar enough that I think that they are not too hard if you solve the homework questions. And if you're not sure about the solution to any homework questions, I'm not excited about writing it and publishing it, but I'm very, very happy to discuss it here or in office hours, or maybe we'll do another review tomorrow. Just tell me what you want me to discuss. Duality. So we have the primal plane, points live in the primal plane, and we have the dual plane. Both have coordinates x and y, but they are somehow in parallel world, if you wish. And the dual also have a dual plane, which is just the primal, obviously. And there is various ways to define how we are, what is exactly the formulas that map objects to objects, but let's pick one of them. I'll take a point in the primal, look at the xy coordinates, and now I'm making a line out of it. The line out of it will be the line px, that is, I'll take the x coordinate of the point, and that's the slope, and I take the y coordinate of the point, and that's the shifting of the line up and down. And similarly, I can take a line and make it a line in the primal and move it into a point in the dual, but just by following this formula. And what is very easy to validate, here are a few points, A, B, C, and D. A is somehow painted. I made them into lines, so I took A and I make it into the line A prime, which just follows the formula. The font is, even in the maximum, the font is a bit small. I need to massage it somehow, but it's not, usually it's A star. Now I denoted it as A prime, but it's Y, which is X times X of A minus Y of A. Okay, that's the coordinate of X star. So A prime is a line, A prime is a line whose coordinates are X times the X coordinate of A minus Y of A. Okay, so I did it for A, did it for B, C, and D, and there are a lot of cute properties that are going to show up, like here is a line that goes through A and B, that L3, I don't need this slide, I have it again over here. Here is a line that goes through A and B. This red line, it passes through A and B. So why are we excited about duality? First, because it keeps above-below relationship, meaning an object intersects with another object in the primal, if and only if they also intersect in the dual. If a point is on a line, then the dual of the point, which is a line, contains the dual of the line, which is a point. I think that it's the first time that I was able to say it. So here is a line L that goes through A and B. What is the dual of this line? Dual of the line is a point L prime. The dual of the red line is a point L prime. And what's so special about the red line? It goes through A and it goes through B. So the point L prime, the dual of the line, is on the line which is the dual of A, the brownish line over here, the dual of A, and it also on the dual of the line corresponds to B. Wait. So it is on the intersection of these two lines. Okay. The duality in this way also kind of keeps above-below relationship. An object A is above an object B if the dual is also, the first is above the other. Well, that's a bit of a lie, the way that we wrote it on the slide. It's actually they are reversing them. So above is just below, but if I just take in the dual plane and take Y to make it minus Y, everything is reversed. I just didn't want to add more formality, and then the relationship are above and below are the same. And of course, being on the line is being on the line. They intersect if and only if they intersect. So now we can play in many, many ways. For example, where is my M? I pick the green point, call it M. It lives in the dual. It's a point. I can look at the dual of this point, which will become what? It will become a line, and the line lives in the primal. But the dual of something that lives in the dual brings us back to the primal. Now, and of course, above-below relationship stays. So remember the brown line, that's the dual of A. Let's put M on this line, and its dual, the dual of M, intersect with the point A, because the point M is on the line, which is the dual of A. Did I say it confusingly enough? Line, brown line, and the point M in the primal, and what happens to them in the dual. Okay, let's see some applications. I think that I can put M aside, and I can put this line aside for a moment. And I need a segment. So I suddenly have a segment. I think I don't need it at the moment. I suddenly have a segment that goes between D and C. Of course, when I move, the point of dual moves as well. And you see the dual of B and the dual of C. And I'm asking you, where are all the lines that cut this segment? Give me a description of all the lines that cut this segment, intersect the segment F. How do I know that the line M prime, for example, intersect this segment? Help. There is a green line, and I want to make it cross this segment.
In the dual graph, the point will intersect the lines?
Which point and which line? To cross? Not exactly, but how do I know that this line crosses this segment? It's not about the lines that go through this segment. That is not the issue. I mean, it's kind of strange to think about it in the primal world. You can guess where duality helps. I put my stick and it crosses the segment. What can you tell me about the ways it crosses it? There are two ways, in a sense, but I can cross it because the point D is below the line and the point B is above the line. That's one way to cross a segment nicely. So if my line is above D but below B, then I cross the segment. And I can also cross it on the opposite direction. And maybe as a point to remind you why it's so useful, you had a question in homework 2, I think, that I gave you a set of points, were blue points and black points, and asked you to find linear programming whose solution would be a line that separated black from the blue from the black. And the solution was trivial the moment that we think about the parameter y equal ax plus b is the parameter of this line, and then ask what limits a and b. That the parameter of a and b are just points, and we can limit it. And from this point, it's becoming a straightforward question. So it's again why thinking about both primal and duality is helpful. So back to my line that crosses F. There are lots of lines, infinitely many lines, that crosses F. Pick one of the lines that crosses F. Let me move M until I'll be, hopefully succeeds to cross F. Voila. I was able to cross F. What did I do with M? Or what did I do with the line, the green line to start with? It is below D, but above B. So if I take the dual of D, which is a line, and the dual of B, how to see, which is also a line, I need to be in between them. One is above me, one is below. That is, in the dual plane, it would be this region. The common name is double wedge. Everything that, so that's a dual of a segment. Double wedge is a dual of a segment. A point that is inside the double wedge, its dual crosses the segment. What is the dual of these two lines? These are the endpoints of the segment. Very confusing, I think. life are a bit easier if my segment is vertical. Here is P1 and P2, and they have the same x coordinate. Help me to understand where all the lines that crosses these vertical segments, what are their dual? Or let's start with what's the dual of P1, what's the dual of P2. So in the dual, here is P1 star, the dual of P1, and P2 has the same x coordinate, so in the dual, it's also a line, but the dual of this one and the dual of this one has the same slope. The x coordinate determines the slope. P2 star. Where do I have lines that crosses this segment? They need to be below this line and above this line, the strips from a fig. So every point here crosses this segment. Why does it look so nice here and strangely enough with P? Is it because for this segment I have two ways to cross it, since it's not vertical. And by the way, the duality business doesn't work. This duality doesn't work if you want lines that are vertical, because then the slope is infinity. Okay, so that was how to find if a line crosses a segment, which now, if you remember my homework over my little question over there, now you can find the line that crosses the maximum number of segments, because it will be the point with the maximum depth. If my segments are vertical, it will just be infinite strips. If my segments are not vertical, then it will be the sequence of double wedges like this, and you ask for the point that is inside the maximum number of wedges, which you solve in the same way. Which is, by the way, how? How do we solve it? Find the point of the maximum depth. You really don't need computational geometry here. But help. N square log n finds the point of the maximum depth. Various ways, but pick one. Well, I'm playing.
On the dual graph, wouldn't it be where like the most segments cross?
Sure, except that I thought that actually it's easier on this part, but yeah, it's kind of equivalent in terms of numerical robustness. There is a difference, I'll show you in a second. But no, let's stay in the pipeline. It's strips, you already have similar question in one of the homeworks, but in this homework, I asked it as queries. There was issues with queries in one of the versions, and a fancy data structure, and a lot of things that you don't need here. So, and you barely need computational geometry. And you can do it with line script, but you don't really need to. Help? Somebody?
Q is the line in the dual and the...
No dual. These are my strips. Find the point of the maximum depth. Here are the maximum depth. Again, I'll remind you, the depth of a point is how many strips contain it. How many geometric objects. So this point is inside one strip, sigma 2. This point is inside sigma 2 and sigma 3, so the depth is 2. I can arrange strips so they all overlap, and so on. So how do I find the point with the maximum depth? So the first step to get it systematically, the first step in computational geometry, what we like to do is that the point of the maximum depth is probably not floating anywhere in the plane. We don't like, even though it can be either infinitely continuous space, we would like to look at discrete spaces. So obviously I can move it until, so if I found some region, some face with a maximum depth, I can move it a bit until it will become, without changing the depth. I can move it until I'll get to the boundary of one of the strips. So I'm at least on the boundary. one-dimensional world instead of two-dimensional. Now I can further move it along the boundary until I hit a vertex. There are not so many vertices. And I think that people start to already zoom in on the solution. So you.
I was going to say, it could be the intersection of the medial axes.
Much simpler. I mean, the medial axis just happens to, the strips are just strips. You don't need the medial axis. It's the simplest question ever asked in this course. Yes?
If you're just looking at the intersections, could you just use the line sweep algorithm?
I can use a line sweep. If somebody doesn't know the line sweep, can you still solve it? Given that it's enough to look at vertices only, that I will tell you. If you're not on a vertex, then you can, without changing the depth, move until I hit the wall, and now along the wall I'll move until I'll hit a vertex. So it's enough to just check the vertices. There is a tiny little trick, but it's enough to just to check the vertices. So if you have n cubed time, then you can generate all the vertices. Strip has two lines. You have 2n lines altogether. The number of vertices is 2n squared. Check for each one how many strips containing it. It will be n cubed. Simpler. Or improve it to n squared log n. And yes, you can do the line sweep, but even in the line sweep, there is something that you need to do. Line sweep is an excellent answer, but it's a question with no main intention, no traps. No. I will draw a little person that is walking on the boundary of the strip. This person is going continuously on the boundary of the strip. It can be during the line strip or separately, but this person has a counter. And this counter is in what is the current depth. So to start with, I am far, far away to minus infinity. My current depth is 1. I'm on one strip. And as I'm walking along the strip, I just hit an endpoint of intersection with another strip. So I'm incrementing my current depth by 1. I hit an exit point from a strip, then my current depth minus 1. So the moment that I sort all the events, and I know for each event, did I penetrate into another strip, or did I just exit from another strip? I'm all the time on the blue strip. I'm not leaving the boundary of the blue strip. But as I'm walking along it, I'm checking intersections, like events, and each one has one of two types. Either I'm leaving a strip or entering a strip, which helps me either increment my counter or decrement it. So all I need is to sort the endpoints along the boundary of the strip, and again. And now just scan it and identify it as plus minus. So that's basic. And of course, you can do it during the line sweep algorithm as well. We'll save. And we will see even faster way to do it. Everybody is cool with this? No techniques that we covered. Okay, so we have the duality transform, the above, below, discussed it. Segment, its dual is a double wedge. Once again, I have the segment PQ, what is common to all the lines that separates P from Q. They are from one side of P star and from the other side of Q star, either below P star and above Q star, or the other way around. That's why double strip. So I separate it only if the line has one of the endpoints of the segment above, one of the endpoints below. There is plenty of types of duality, and they are like adding more insights over here that I want to show a bit more. I skipped this slide. We talked about convex hull. So what happens with a convex hull? Actually, I have a set of lines, and I look at the upper envelope of all these lines, what is above all these lines. We talked about upper envelopes. They played a nice role. If you remember in the Voronoi diagram, we showed how we can take the Voronoi diagram, make it into planes by two transformation. First make it the value square, and then subtract x squared plus y squared from all of it. So every point they made a plane, and then we looked at the lower envelope of all these planes. And by the way, if we look at the upper envelope of all these planes, for the Voronoi diagram, it would be the further side Voronoi diagram. Not the closest side Voronoi diagram, further side Voronoi diagram. Back to our setting. I have a set of lines, that's my input, and I pick on one of, I pick on a vertex. First, I take all these points and I dualize them. I start. I look at all these lines, for example, L1, and I think about the point L1 star, the dual of L1, and the same goes for each one of the points. Here is the dual region of all the points, and if there is any line in the world that is below all these points, this line is below all these points. Where is its dual? In the picture, where do you see the dual of the picture if I hold the stick right here?
It's in the envelope.
It is, or even above. It is above all the lines, above, below, change. Here, my line is below all the points, so it's a dual. The dual of the line is above all the lines. What does it mean to be a vertex over here? This vertex is on two lines. So the dual of this vertex, is a line with a property that it goes through 2 points, and the remaining points are above it. So basically, the dual of the upper envelope, or the dual of the vertices of the upper envelope, is the lower convex hull, and this is the upper convex hull. Okay. One more cute property, and then we'll move to the review. So let's put this point aside. Everybody understands. Oh, sorry. Now when you have this observation, we talked about it last time, then if I'll give you a set of half planes and ask what is below all these half planes, you know how to do it. In linear time, if they are sorted by slope. One way was the Holmholtz equation that asks if you have a half plane given by an increasing slope, then you can do a tweak with a stack and maintain the lower envelope. Or you can just dualize it to a set of points, compute a convex hull, and and the upper envelope and the lower upper envelope are just their dual is the upper convex hull, lower convex hull. Questions about it? Is it clear? Okay. Okay. Once again, primal dual. I don't need this segment anymore. Let's think about the point A, and let's think about the angle A watches B, C, and D, and they are arranged in some order. Like, if you remember when we asked ourselves, how do I compute the visibility graph? I have a set of obstacles, each vertex needs to ask what are the other vertices that this object sees, and the algorithm was a circular sweep. I was rotating a ray around me, and every time that I had an event, I asked, what is this event? Is this relevant because it's an edge that I need or I don't need to add this edge to the visibility graph. But it all started by I'm a corner of one of my obstacles, a corner of the table, and I rotate a ray around it and ask, at which order do I see other objects? This circular sorting by circular order. So let's think about the point A, and A, C do this circular order, circular sorting. At which order does it see the rest of the points? It sees B, and as I'm moving counterclockwise, I'll see C, and then I'll see D. Okay. That's the order at which A sees them when A just look at this direction. Okay. How is this relationship, this order, express itself in its dual? It's kind of cute. So the dual of this is the brown line is the dual of the point A. So this is a point N that is moving along the dual of A. As long as N is on the brown line, then the dual of N is a line that passes through A. What about the orientation of this line? Since I'm moving along the line from left to right, my x-coordinate increases. It means that the slope of this line increases. What are the events that happens every time that the dual, this direction that I see, goes through one of the points? Just means that I'm going through a vertex with one of the other lines, bringing us again to something like this. You want to compute the visibility graph. One of the ways to compute the visibility graph is look at the dual, and now for every line, ask at which order does it hits the other line. The order that it hits the other line is exactly the order that the primal point sees the other points when it rotates around it. Okay. After the midterm, I'll tell you about half transform. That was a big commercial success that uses duality for computer vision, or Google for it, half transform. It's a bit low level, 1960s, 70s vision, but the basic idea behind it was that if I have an input which is, I have a lot of points that you see, but some of them are along the line because it's an edge of the building or something. And there is a lot of noise. No point is exactly on the line, but there is a lot of points close to the line. And I want to find what is this line, given that only 10% of the points are on the line and 90% of them are just noise. So I cannot do any majority or something. So half transform says I'll consider all the possible lines, except that I'll dualize them. So I'll discretize them, sorry. So by discretizing, it means I'll only consider special orientation and special parameters, and just do a voting. Hey, a line, are you going close to this point? We're going close to this point. We're going close to this point. And essentially, you're just saying for the correct lines that go through 10%, it got many votes for many points as it's going next to them. So it just becomes into, let's take the dual plane, put counters in the dual plane of how many points satisfied a line that is dual to a point in the dual. But as I said, I promise not to tell you. What we can do now is just go skim over the slides or go to the questions that I asked you. But before that, if I'm available tomorrow 7 to 8, if you guys interested, great. We can have Zoom something. If not, it is fine. So, and you can tell me tomorrow. But anything else that you want me to do beside there? Go through the slides really quickly. It's a very large file because I did add and it's a large file, and I still covered only some of the materials, but okay. Yeah, let's start just in a moment to remind you that even if you're doing well in the midterm, etc., and even though my formula is very friendly for people that had difficulties in some part of the semester and harder time in the other, even if you are only aiming for X, whatever X is a letter, and you got it secured, you're not getting it secured if you're doing really, really poorly at the final. There is a limits in the final that I computed that you cannot just forget in the end of the semester. I don't want to go to the final at all. So there is a minimum grade to get a B in the final itself. Okay, but check the formula exactly. It's nothing known. I think that it's very friendly. Nobody. Okay. At some point at the beginning, we discussed algorithms to know if a point is inside the polygon, and it was a cute trick that we used in several parts. If P is convex, then I can find if it's inside by doing binary search on the vertices below it, binary search on the vertices above it. Now when I find the edge, Zoom is unhappy. Okay. Team, can you still see me? Or, okay. I hope that. Okay, thanks. Yeah, good. So if P is convex, we had plenty of solutions, but that was the first one where convexity helps. If you have all the vertices arranged in any sorted way, then you can decide, I want to find what is the edge below the line. Again, the edge just vertically below P. How do I do it? There is a vertex whose x is to the left of P. There is a vertex whose vertex is to the right of P, and this one are consecutive. That is, it's an edge, so I can generate the edge if I know the coordinates of this vertex and this vertex. I can then generate the y value where the vertical line y equal to y of P. The vertical line crosses a polygon at this edge. I can find what is the y value over here, what is the y value over here, and what is the y value of P. And it's kind of easy to find if P is slower than the maximum, but higher than the minimum. So convex polygon, it's fine, and it was our first example of binary search. If P is non-convex, then we are spending linear time by shoot any ray down, find the intersection point with this way. They don't need to be sorted, but to understand the proof, we imagine that we sort them, And then we're doing this, working on the boundary trick. Start from minus infinity, and your first intersection means that you just enter P. Your next intersection, you just exit, enter, exit, odd or even, you got it. You know if you're inside P or not based on a parity. Okay. We played a lot with convexity. We talked about convex Hall for a long time. I never told you, and I still don't tell you, if convex hull, I mean the boundary of the convex hull or the segmented. Create this polygon or all the point inside. It's depending on the context. It's clear which one I refer to. Since it's a simple polygon, it doesn't matter, and you have plenty of definition of what is a convex hull. Two definitions that were actually, or a few definitions that were actually useful for us is the intersection of all the half planes that contains the shape, intersection of all the half planes that contains the shape. We played with this last meeting. We played with this in linear programming, or the complement what you're getting by raising all the empty half planes that don't contain the shape. That was kind of introduction to alpha shapes, but alpha shapes are not in the middle. Okay, so it's clear what is a convex hull, and a lot of cool things happen along the convex hull, like that the orientation of the angles comes at an order, right? That if you're walking around it, the orientation comes with an order. I did want to highlight what is a convex combination that we saw several times. So far, a convex combination, I have a set of points, P1, P2, P3, P4, and I'm giving some weight, Wi, to each point, Pi, it's vector sum, and I look at sigma of Wi, Pi. And, it can be a lot of things. There is some point in the plane that correspond to it, but if I'm also making sure that all the weights are positive and they sum to 1, then I call it a convex combination. I call it a convex combination if they sum to 1 and they're all positive. And what are all the points that I'm generating in this way? It is just exactly the convex hull. How can I prove it to you? I can prove it in many ways. For example, I can say you remember it for a triangle. You know that it's true for along the segment, you'll just need 2 weights, which are non-zero. That sums to 1. Along a segment, it's just a linear combination of the 2 endpoints of the segments based on the weights. Then you can make it into triangles. Then you can triangulate the polygon and say each such triangle I can give it in the weight. But don't forget what are barycentric coordinates that we used intensively when we talked about mesh generation. So it's already a problem. Okay, sorry, what did I skip on? All the half planes, and it's the shortest perimeter set that contains everything. Problem of robustness, remember it, we don't like to divide things. Division is bad for us because we are not guaranteed that when we are doing the same division, we'll get the same answer. Even though algebraically we expect to do the same answer, but in the real world, taking x times 1 divided by x, that is, I'll compute what is 1 over x and multiply by x, can give me one result, while taking 1 over x, if x is varied, 1 over x times x might lead me to different results. That is, in short, I'm trying to say that x times 1 divided by x, if x is extremely tiny or x is extremely large, this is not guaranteed to give me 1. And it's in geometric setting, when you're talking about angles around it, then it might be a real issue. That's this geometric issue. You can, what you think that is a convex hull might be not the convex hull, which is not terrible, but can also be part part of the polygon which is not closed at all. You didn't run all the way around the set. I didn't show you this slide because we were still in the upper room. I have 3 points, P1, P2, P3. Am I going counterclockwise or am I going clockwise? I can get the answer robustly by taking the coordinates of everything, put them into this formula, which is coming from this determinant, which comes from the cross product, and the answer that I'm getting from this is just the area of the triangle, except that it could be positive or negative depending on did I go clockwise or did I go counterclockwise. If I'm going counterclockwise, then it will be positive, and if this formula is 0, it just means that the 3 points are collinear. Okay, yeah. A Gram scan, putting all the points in a stack, and every new point might recheck the new point, the point before it, and the point before it. Are they creating a right term? That's when I'm creating the upper convex hull. But I'm asking, did I create a right term, or did I create a left term with a new point? The previous one, I forgot to say, but remember it, that I scanned the points from left to right. I sorted them somehow based on the X, and this event where I have a left term might cause me to remove some points from the stack, and possibly a lot of points from the stack. But it's still only linear because the point can be inserted to the stack once, can be removed from the stack once, and once it's gone from being considered to the upper convex hull. Okay, you have the code for it. If you want, and the other convex hull that is, in terms of method, it's much more general, but it's inferior to Gram scan. In this case, is divide and conquer. Partition the set into 2 subsets, compute the 2 convex hulls to the left or the right recursively, and now merge them. And the merge them kind of brings nice geometry into it. Merge them, I had to find out what is a common tangent to the 2 sets. There are 4 common tangents. I care only about 2 of them because these are the 2 edges that I need to add to make it the convex hull of everything. And I kind of skimmed it that you can find the common tangents by starting from some arbitrary pair, and then I'm doing kind of chicken walk, either a bit to the left or a bit to the right until I'm converging to the lower convex hull, and similarly to the upper convex hull. So that was another n log n. Why am I making such a big deal about this algorithm? Because we use similar method to compute union of objects. We can use it to compute Voronoi diagram of set of points. We didn't talk about it much, but I can compute Voronoi diagram of a set of points by compute the Voronoi diagram of the left set, compute Voronoi diagram of the right set, and then if you can do line sweep or something and merge the 2, which you can do in n order n log n time, then you just need log n many steps in your recursions. Or compute the unit, the free space, or compute a few things that divide and conquer doesn't have. Okay, and finally, the third algorithm for computing. Convex hull was a gift problem, which is also an important algorithm. How does it work? Pick the lowermost point, and then do circular sorting. Basically, you are looking at the visibility graph of this point there at the bottom, and ask what is the rightmost point that I see. That would be an edge of the convex hull. Okay, so I just discovered the first vertex of the convex hull, the lowermost point, if it's unique, must be, and then I can go around it and discover all the poles. Why is this important? Because I asked you in the homework to find a linear programming that works in arbitrary dimension that ask, hey, point, am I a vertex of the convex hull or not? And the solution in higher dimension was very similar. I'm a vertex of the convex hull only if I can find a direction or a plane for which my maximum value in this direction is larger than the maximum value in every other direction. So you just needed for each vertex to run one linear programming algorithm, and then you knew is this a vertex of the convex hull or not. And you can do 2-dimension or 3-dimension gift swapping around your shapes. That's quite close to how people compute convex hull in higher dimensions. Another reason to put some importance on it is that it's output-sensitive algorithm. Right? It sometimes runs fast, sometimes runs slow, depending on how many vertices you have on the convex hull. But in this simple algorithm, it's linear time per vertex. Okay, and we mentioned that you can, if you can solve convex hulls, then you can also sort, but you cannot sort in time better than n log n. I didn't make big deal out of it. Line sweep algorithm talked about intersection of segments, and how do I find intersection of segments? I can ask, do the segment cross? And I can ask, where do they cross? And it's a different question. I can answer one robustly, but I cannot find the intersection point robustly. I have a set of segments, which is, again, just an excuse to study line sweep. So many other applications than just segments. I want to find all the intersection points. Main ideas that you want to highlight is that you are sweeping the plane kind of continuously, but it's really not really continuous. It's enough that I'll think about combinatorial change versus geometric change. If I'll take my stick and just move it by a slight amount, but my stick still cuts the same segments, maybe not exactly at the same y value, but the same order of segments, the same set of segments, there is no combinatorial change. Combinatorial change would be when I stopped intersecting one of the segments, or start intersecting a new segment, or that the order of two segments change. I'm not going to ask questions like, what is the definition of combinatorial change? It's a bit in the eye of the observer, but I think that from the context it's clear what's the difference. Slight perturbation of the segments, the y values change a bit. I don't care when the status, who do I cross or at which order changes, that in this case, what I call combinatorial change. So we notice that nothing important changed from one event to the other, so I just need to jump from event to the other event. High-level idea, instead of looking at static two-dimensional image, I prefer to look at dynamic changing but one-dimensional image, what the line sweep knows. And then we had essentially two data structures. One was all the events that I know about in the future, all the events that I know about in the future, which are all the starting point, ending point, and some of the intersection points that will exist in the future. Like at this moment, I know that this will be an event. And it's an event because there is a combinatorial change to change, segment change. And I know about it and put it in my data structure to discover next. And the other data structure was a balanced search tree that contained all the segments in the same time. Okay, I think that you mostly have it. I kind of summarized the slides a bit, so the slides here are a bit more compressed. We use successor and predecessor relatively, and the big idea over here is if you have an event, then you have across the status. You have an event, then across the status, you have new pairs of segments that might or might not intersect. But at most two such pairs. No matter which event, at most two pairs of segments might are suspicious that I didn't check them already, so I check them now and see if they intersect in the future. Okay, and each time that I had to do it, it was a few operations in the data structure, but the time analysis, the high-level time analysis was that you are spending log n time, constant number of accesses to each one of the data structure, log n time per event, and the number of segments, and how many events do I have? At least 2n for the endpoints, plus k, which can be anywhere from 0 to n squared, k is the number of intersections. Why is this so important? Because we used it recently, even though it's not in the material in the motion planning. We used it in several of the homeworks parts, right? You want to compute any overlay of maps, shapes, DCL, images, each one of the shapes that we studied. I can always do line strip when they are in the plane by taking some subsets, compute. Say if I'm talking about the union, take the union of the first, take the union of the second, and now merge them. The same goes for lower envelope of planes or paraboloids or anything that lives above you but is projected on the plane. Don't forget the relationship between lower envelope and Voronoi diagram. And in the review, there are two questions about this, exactly this trick and how it's related to weighted Voronoi diagram. Okay, my favorite diet, linear programming. There will be infinitely many questions that I can ask about linear programming. In the 545, I asked recently, look at these strips, and now look at parameter. You don't see it. So let's do it really quickly. Now I do look at the skeleton of the strip, and I say the size of all the width of all the strip is some number h. Another strip whose width is also h. H is from the skeleton of the strip, the middle axis of the strip, all the way to the boundary. My question is, find the minimum age such that all strips have a point in common. Their intersection is non-empty. Help? Talk to each other. Let's take 2 minutes. It will wake you up. Get a little group, solve this question. Is the question clear? I start from a set of lines. What I'm given is a set of lines. L1, L2. I take L1 and I do the Minkowski sum with a ball of radius r. Minkowski sum with a ball of radius r will create a strip, and the width of this strip, forgive my poor drawing, the width of the strip is 2h. The same goes over here, 2h, and fine, and probably unless all the lines, the input line, unless they are all having a point in common, probably if I take h to be 0, the strips don't have any pointed lines in all the strips. There is no point in the intersection of all the strips. If I take h enormous, the strips cover the whole plane, and obviously they all intersect. Find the smallest h, it's like the center there. Anybody sees it? I think about it as an easy question, given what I tortured you is earlier in the course. And yeah, check it out. Oh, yeah. In expected time over n, which is already a big hint the moment that I said expected, we saw two randomized algorithms. The Illinois triangulation, where I inserted the point at random, more complicated, and the linear programming, where I insert the half planes at random order. So expected is like a sign. One of these two algorithms is relevant, and I don't see how it's related to the Illinois. Linear programming. So linear programming goes here. Variables, constraints. Okay, I'll change the problem a bit just to make it a bit easier about age. Let's say that age is actually vertical. So this line, if the middle axis is y equals ax plus b, then actually in the question I'm asking that the lower line is y equals ax plus b minus h, just remove it downward by h. And this one would be y equals ax plus b plus h, to put it on the top. Variables, how many dimensions, how many variables? Three. X, y, and h. Cost function, minimize h, minimize this width, such that x, y belongs to sigma I, each one of the strips. This is not linear programming, of course. It's not linear constraint, but it will be in a second. What would be the linear constraint? Look at this formula. The point x, y to be at the intersection needs to be above this line. So x times ax plus b minus h should be below y. So for this x, let's take this x, look at the x value, look at this x. So this, now I'm getting the result of this formula, this point over here, should be below the y. So y is large or equal y is above this line, and y from the similar argument is below ax plus b plus h. And that should happen for every one of the lines, so it's a, I, b, I. QED. That's it. What's the worst case time of this algorithm? Expected time is linear, because how are we doing it? We are adding the half planes one by one. We forget about it. They come from different strips and so on. It's just a bunch of half spaces, sorry, not half plane, half spaces, constrained in 3 dimensions. And we know that the expected running time of linear programming in low dimension is linear, using the incremental algorithm. But the incremental algorithm can have a really bad day. It's 1 over n factorial the probability that you have such a bad day, but it's possible. And if you have such a bad day, then the answer was you will.
Now for this one,
for the sake of time, I'll just shoot it out in 2 dimensions. Let's say that age is fixed. I just want to find x and y that will be in the intersection. So, important point, I want to find x and y in this intersection. The way this algorithm works is that it wants a cost function. It wants a cost function. Which one, if I just want to find feasibility or not, it doesn't matter which cost function I'll pick, but it assumes that you picked some direction, say downward. So I'll try to minimize y. Now I have only 2 parameters, x and y. I'm trying to minimize y given all these constraints. And the expected running time is linear. Expected what? When I create random permutation. How do I create a random permutation? We talked about it. Pick random elements, put at the end, take the element at the end to this random location, and shrink your array a bit, and keep doing it, kind of like a bit similar to a heap sort, except that the element that you put at the end is at random. Anyhow, that's how you are inserting them at a random order, random permutation. Say it's kind of rare that we have to rearrange to solve the one-dimensional linear programming, but there is a chance of 2 over I to be precise. We'll get to this slide in a second. And if it does, then if things don't work well, then in 2 dimensions it will be n squared. And you should all remember how to create an example where it is order of n squared. Just every new half plane that I'm adding contradicts, disagree with the previous best solution that I had. For example, this and this will be my first two, and now every new guy that I'll add will force me to take 1 point above it. And similarly, I can do the same deal in 3 dimensions, where what happened in 3 dimensions, every time that I violate the previous optimal solution, I have to call the 2-dimensional linear programming that in the worst case takes, we just said it, the worst case takes theta of n squared, and in 3 dimensions we might do it n times, so it's n cubed. Okay. Similar discussion, analogous discussion about why it is okay to only look at solutions that are only at vertices, why we don't need to worry about other functions. Like a good example question would be, it is true that if my cost function is minimize y squared, it is still correct that I can look at vertices only. Not really, because if you look at a parabola, the minimum might be somewhere floating in the middle of the feasible region. It's a convex programming, but not there. But I don't enjoy the luxury of just check vertices only. Okay, I can check only vertices. Simplex algorithm, don't forget. Simplex is what we really want, the algorithm of Danzig. And in 2D, remember, we started from the 1D linear programming. How do I solve it? If somebody told me, just look at the solution on this line, you still have half planes, but look at the solution only on this line. Just find maximum of the mean, minimum of the max, and see if one is above the other or not. And if not, then you can also say the feasible region on this line is empty. There is no answer along this line. And that's linear algorithm, worst case, nothing randomized. That's how it looks if this line is just oriented somehow and not horizontal, but conceptually the same. I have half planes that looks up, half planes that looks down, and I just compute the intersection points with this line, and take the maximum and the minimum once again, and say every point along this segment, you don't see it, every point along this segment is at least feasible as much as I know right now. Okay, so if I go, and one of the two endpoints of the segments are the solution. Incremental algorithm, don't forget, you don't maintain the whole feasible region. It's tempting to be a midterm trap question. You do not need to maintain the whole feasible region because it can go through n-squared changes and you don't care. You just care about what is the optimum vertex. That's the only thing that you keep in mind. And now you're adding one half plane, one at a time. And you ask, does it violate when I'm adding hi if the previous optimum solution is on the new constraint? And we are happy because if it's not broken, I don't need to do anything. It's also the optimum after hi is in the game. And just call the new optimum what used to be the old optimum one half plane ago. If that's an unpleasant case, if the previous optimal solution does not agree with the constraint that you are just adding, then you're solving the one-dimensional linear programming where you just look at the solution on Li, on the line that bounds hi. Why convexity? Important point, you have a review question about it. Convexity, Cat will tell you, it cannot be that if you're adding one half plane, the brown half planes that you see over here, hi, here is vi minus 1, the previous optimal solution. Here is vi somewhere in the feasible region of all the half planes, including hi. If this is a new optimal solution, it must be on the line that defines hi. It cannot be just floating in the middle at the interior of hi. Why? Because of the cat and the perimeter of the Earth. Keep walking in this direction from the new optimum to the old optimum, and obviously the old optimum was better for you, and if you're going in this direction, you'll just improve your cost function. So that was important, and one of the big conclusions was if you got to call the one-dimensional linear programming, and it's not true in general that if you call the one DLP and you didn't find solution on this one particular line, it doesn't mean, of course, it's important and interesting point. Here is my feasible region, defined by these guys. These half planes, and I call the 1DLP with respect to the red half planes, and I don't find on the red line any optimal solution. Right? There is no solution that is on the red line and also inside all the green half planes. So that's not an indication that the feasible region is empty, that there is no solution at all. But if you followed all these directions, you call the 1DLP just if nothing else failed. You did not have any, you had the previous solution, it did not work for age I, it violated age I, so then any solution that you find must be on the line. Yeah. And the n square and the brilliant analysis of how do we know what the probability that we need to call the one-dimensional linear programming. Well, let's assume that I put all the n half planes all together, they are all created there, and then I'll pick one at random, like I reverse time. They're already all in, and I pick one at random. There are I constraints altogether, only two of them define the minimum. What's the chance that I remove now, reversing the insertion, reversing time? I just remove one at random, it's the opposite of add one at random. What's the chance that I'll pick one of the two bad half planes? 2 over I, because that's the number of half planes that they find, the minimum. Okay, 3D, just that you're just doing the same thing, just if you need to call LP, then call it in 1D. We played a bit with ILP. I might ask about it briefly. It was not a big topic for us. I spent more time on it in the other parts. We saw how ILP can help us find, say, vertex cover, set of vertices that hits all the vertices. We saw how it can find us the mean weight, and an example that I did make a note of myself to remind you that we did see as one of the examples of ILP is the solution to the art gallery problem. I want to find the minimum set of vertices that sees the whole polygon, sees every vertex of the polygon. How can, using ILP, how can I do it? For every vertex, K, I will compute what are all the vertices of the polygon that K sees. For every vertex X, small k, I specify if xk is 1, then I'm using this vertex I, as part of my guarding set. And if xi is 0, then I will not put this vertex in my guarding set. What's my set of constraints right now? I want to pick every vertex that I put as a guarding set. I need to put a camera. It costs me money. I want to minimize how many vertices I need to guard the whole polygon. What do I do? For every vertex k, I ask what are the other vertices that k sees, or other words, what are the potential guards that I need to pick in order to keep k covered, to have somebody looking for k. Here is a set of all the vertices that k sees or they sees k. For example, yg or age or everybody in this list are all the vertices that k can see, and k does not see p. So if I put a guard at p, it will not help k1. I need to put a guard in this part. So I want to minimize how many vertices I pick, subject to, for every vertex k, somebody in the visibility guard of k must be picked. Otherwise, this vertex small k, sorry for k and small k, otherwise small k. Vertex small k will not be guarded. And this should be true for all vertices. And from now on, you just let the ILP find the solution for you. Graph definition, we talked not much about planar graph. It could be connected graph, embedding and not embedding. I didn't make much deal out of it. That if you can draw it as a planar graph, you can render it as a planar graph, no edge crossings, and you can also do it with straight segments, non-trivial theorem. We talked about triangulations, how many triangles, and of course, and the Euler formula that we are using a lot, various constraints. The big highlight of Euler formula is that if we know that the number of faces is linear, number of faces in the map is order n, like the Voronoi diagram is a good example. Number of vertices, and one of the homework questions, not homework, review question, exactly ask about strange Voronoi diagrams where still number of faces is linear, which will tell you also the number of vertices and number of edges is linear as well. Usually when Euler helps us, but we also used Euler to know that the average degree is 6, which also helps us when we are going to paint maps, another question from the review. How do I know that every map I can paint with 6 colors? In a way that every country, every state will be a color, and 2 states that are neighborhood that share a boundary will have different colors. How do I do it? I look at the dual graph, 2 states that are next to each other are connected by an edge. There must be a vertex of degree 5. The average degree is less than 6, so somebody must have a degree of 5 or less. I look at this state, eliminate it. There are many states that I eliminate this state, and now look at the remaining graph. There is now somebody with degree less than 6. Eliminate it, eliminate until you are left with a single vertex. Give it a various color, whichever of the 6 that you want, and start putting vertices back. And at every moment where you're adding a vertex, at this very moment, this vertex V that you're adding is connected only to 5, at most 5 other vertices. No matter which colors I gave to these other 5 guys, there is always a color that I can paint V without contradicting any of them both. So, should we continue tomorrow? I mean, I got a bit more steamy few guys, but up to you. No, I don't find too much enthusiasm. And homeworks vary in difficulty. The Midterm will vary in difficulty, but it's definitely not. I don't get any brownie points of show how hard they can make the Midterm to be. That's supposed to be fair. No, but it's not going to be also MIT somewhere in the middle. But I thought that this, now what might make it difficult is that there is material in the book, and then there is other things that I added, like the crust algorithm, Romenta, is not in the book. And I asked questions about it here. The linearization, it's barely mentioned in the book, but you're using